Now we're going to look at a transportation problem that is more generalized. The previous transportation problem we saw was you had a bunch of origins and a bunch of destinations, and transportation took place strictly in one direction, from origin to destination. So what if transportation is possible in both directions, which is more practical? And that's what we're going to look at here. So here in this example, we have again three origins, three sources. So this S here means source, and these are the capacities. And the arrows show in which direction transportation can take place. So here we have arrows on both sides, so you can have a transportation going from 1 to 3 or 3 to 1 as well. And same here and same here. Then if you have an arrow like this where there is an arrowhead only in one side and not the other, so that means transportation can take place only in one direction. And here the T means it is a transshipment point. In other words, this is like a warehouse. So in a warehouse, quantities come in and go out, nothing stays here. So what comes in must go out, so the net value should be 0. And these are the destinations, and these numbers indicate how much demand there is. So what comes in net must be equal to 400, because this arrow here indicates that some of what's coming in can go out as well. Now for each of these arrows that we see here, there is a cost associated and that is given in the next page. Okay, so here are the costs. Now we need to set this up in Excel. So let's go to Excel and set up the. So here is and there is a common arc capacity of 200. You cannot ship more than 200 units in any given arc. So we have the origins, destination, and we need to set up the unit cost. Okay. Well, we need to go back to the problem. Then see, we have from 1, we can go to 2, 3, 4, 5, 6, and 7. So it can go to all the other nodes from 1. So we need to set up 1 to 2, 1 to 3, 1 to 4, 1 to 5, 1 to 6, and 1 to 7. So same way like we did in the previous problem. And the costs then are 5, 3, 5, 5, 20, and 20. And then we do the same thing with 2. And from 2 you can go to 1, 3, 4, 5, 6, and 7. Again from 2 you can go to all other nodes. So from 2 to 1, 2 to 3, 2 to 4, 2 to 5, 2 to 6, 2 to 7, and we need to enter the costs for those here. And I have done this for all the arcs, and that's given in model. So let's switch to this sheet. Okay, so we have everything set up. So let's color code these. Common arc capacity is an input. So let's give a name to that. And the unit cost is an input. And let's give name to these 4 columns. Okay. And flow is of course the changing cells. Let's color code that like that. Now arc capacity is that. So let's copy. And we need to make sure that the flows do not exceed the arc capacity. Okay, so now let's give a name to arc capacity. Okay, now we need to set up the node balancing constraints. Okay, now unlike the transportation problem when the transportation took place only in one direction, so here transportations can come in and they can go out as well. So we have to calculate the net outflow. What is the net outflow? So you have to look at how much is going out minus what comes in. That is our net flow. Okay, that should be less or equal to the plant capacity. So here we need to first do a sum if with origin, okay, with the node number as the criterion, and we sum the flow. Now this will give us the quantities that are flowing out, and you subtract what is coming in, so that will be sum if for the same node number, but you look at the destination and then you sum the flow of that. Okay. So that will give us the net outflow, and the net outflow should be less than or equal to the plant capacity, and the plant capacities are given. So let's enter those numbers: 200, 300 and 100, 200, 300 and 100. So these are input values. Okay, so now we can copy that. Okay. Now warehouse, okay, and we can copy the same formula from here down here. The warehouse nodes are 4 and 5. Okay. Now that should be equal to 0, because what comes in must go out, so the net flow should be 0. Now in some instances, if it is a continuous stream of material or processing plant, there may be process losses. Okay, if there are process losses, then we have to adjust for those. So that should be 0 there. Okay. Now for the destination constraint, destination nodes, which are 6 and 7, again we can copy the same from here. Now except that in this case, what we want is the net inflow. Okay, what is coming in minus what is going out. So the plus and the minus should be changed. So this should become a plus now, what is coming in, and what is going out should be negative. So you subtract what is coming in and minus what's going out. That stays right at the destination, and that should be equal to the demand, and the demands for the two destination points are given as 400 and 180, and these two are input values. So let's color code it like that, and we copy this. Okay, now let's name these. Okay, there are these three on the left side, and we don't need a name here because we can just set it equal to 0. Okay, then finally we have total cost. So total cost is some product of cost, unit cost, and flow. So that's our objective function. Now let's run solver. Total cost is the objective function. We want to minimize that. And flow is the changing cells and the constraints. So we have the net outflow for the origins must be less than or equal to the plant capacities. Now for the warehouses, the net outflow or net inflow should be equal to 0. What comes in must go out. And for customers, the net inflow must be equal to the customer demand. So these are the three basic constraints. And in addition, we have one more, which is the flow must be less than or equal to the R capacity. We can enter the common R capacity as the right hand side from here, or we can enter this entire column. Okay, so click OK, make non-negative simplex, okay, and then solve, and we have the answer. Right. The flows are shown here, and zeros means those flows do not happen. So we can go back to the network and we can drop all the arcs with no flow and look at what transportation is actually taking place. So here we have retained only the arrows where there is flow. So we have a flow of 180 here, and then these are the flows from 2, these are the flows from 3, and then 4 to 6, 5 to 6, and then 6 to 7 is 180. So these are the flows that Excel found, which is the cheapest transportation plan.